which I thought I should discuss after we complete the antenna portion and the waveguide portion. One of those portions is the Smith chart. It is a graphical tool. We will discuss about this graphical tool today. This tool is called Smith chart or Z chart. We are going to discuss about this. I hope that you remember the summary of transmission lines. So we'll start with that. First, let us look at the transmission line. So here we have a transmission line whose characteristic impedance is Z0, propagation constant beta, and voltage on the transmission line at any point Z is Z and Vz. Transmission line is terminated on a load ZL, terminated at Z is equal to 0. So termination point is Z is equal to 0. So from that point, that is the load point or the termination point. Then from that we move in the leftward direction towards the generation point. So if that is Z is equal to 0, as you move towards the generator, Z will be negative. Current on the transmission line is IZ. So at any point, the dashed line shows a point on the transmission line. At that point, current that is at a distance Z from the termination, Z is equal to 0. Current is IZ, voltage is Vz. Characteristic impedance is Z0. Propagation constant is beta. It is a lossless transmission line, therefore propagation constant is beta. We are going to consider this transmission line. For such a transmission line, if we consider such a transmission line, unlossless transmission line, then the voltage at any point Z, so reference point we are taking at Z, so at that point voltage is V0 plus exponential minus gamma Z into 1 plus capital gamma subscript L exponential minus J to gamma Z. I hope you remember this. Otherwise, you can just expand this. If you expand this, you will simply get V0 plus exponential minus gamma Z, that is representing the forward propagating wave, then plus gamma L into V0 plus. Gamma L, you know, is equal to V0 minus by V0 plus. So gamma L into V0 plus will be V0 minus. V0 minus is the reflected voltage. V0 plus is forward propagating voltage. So that term will give us V0 minus. For V0 minus, we can also write gamma L into V0 plus. Gamma L is the reflection coefficient. Gamma is the reflection coefficient. Gamma L is the reflection coefficient due to the load. So that is gamma L. Then exponential minus J gamma Z into exponential 2 gamma Z. So that gives us exponential plus gamma Z. So that part is second part. So V0 minus exponential gamma Z, that gives you the forward propagating wave. So that we can also write as V0 plus exponential gamma Z, exponential plus gamma Z or minus gamma Z, whatever you take, into 1 plus gamma Z. Will drop the L load, that will drop for simplicity. So that will write as gamma Z. Now what is gamma L? How do you define gamma L? Gamma L, as I told you, now V0 minus by V0 plus, or reflected voltage by the incident voltage. That also can be written as ZL minus Z0 by ZL plus Z0. ZL is the load impedance, Z0 is the characteristic impedance of the transmission. So if you know the load impedance and characteristics impedance, we can find out gamma L using this formula. This we already have seen when we discussed about transmission line. Now this is the expression for Vz. Similarly, for Iz we can write Iz is equal to V0 cross by Z0. As you know, I is equal to, or V is equal to I into Z. Therefore, Iz is equal to V0 cross by Z0 exponential minus gamma Z into 1 minus gamma L exponential minus 2 gamma Z, cross 2 gamma Z. That you can write as V0 cross by Z0 into, V0 minus by, V0 plus by Z0 into exponential minus gamma Z whole into 1 minus gamma Z, capital gamma Z. We have just simply dropped the L for simplicity. Then Z, which is the input impedance or impedance in from the load side, from the source side or generator side. So input impedance at the point Z is Z as a function of Z is equal to Vz by Iz. That we have found out is equal to Z0 into 1 plus gamma L exponential 2 gamma Z divided by 1 minus gamma L exponential 2 gamma Z. Now drop the subscript L, that gives you Z0 into 1 plus gamma Z by 1 minus gamma Z. And now gamma Z, we know what is gamma Z is equal to gamma L exponential minus 2 gamma Z, and that is equal to ZL minus Z0 by ZL plus Z0. Here this gamma Z is called the generalized reflection coefficient. So gamma Z is equal to gamma L exponential 2 gamma Z, that is the generalized reflection coefficient in this expression. So remember this. Then we are going to discuss about the Smith chart, or try to find out the derivation for the Smith chart. Before that, let us see what is the importance of this generalized reflection coefficient, which is gamma Z, that is equal to gamma L exponential of 2 gamma Z. So gamma Z is equal to gamma subscript L into exponential 2 gamma Z. That we can write in terms of absolute value. So if I write absolute value, gamma L is in general a complex number. If it is a complex number, it can be written as an amplitude into a phase part. So magnitude part, phase part. Magnitude part will be the absolute value of gamma L. So that is gamma L absolute into the phase part. Phase part of gamma L is exponential j phi L. So that part remains, that is the second term. So absolute gamma L exponential j phi L, and exponential 2 gamma Z remains as it is. So that also you can write, since gamma Z is a complex number, we can write it as in the form x plus jy. Here we will write the real part of gamma Z as gamma rz plus the imaginary part of gamma Z as j gamma iz. So this is how we can write. Now if we have a lossless transmission line, in the lossless transmission line, alpha is equal to 0. You know, gamma is equal to alpha plus j beta, and alpha is equal to 0. Since alpha is equal to 0 in a lossless transmission line, we can write now gamma Z is equal to absolute gamma L into exponential j phi L into exponential 2 j beta Z. Now take j common. If we take j common, then this becomes absolute of gamma L exponential j into phi L plus 2 beta Z. So remember, there are two terms in the exponentiation. One is phi L, which is the phase of gamma, or phase of the reflection coefficient, and there is the other term is 2 beta z, which depends on z. So depending on z, this e to the power j 2 beta z will vary at different points. Gamma z will be different on the transmission line. That shows that gamma z will be different on transmission line at different points. That comes from 2 beta z, and the constant phase term is j free L. So that will always be added to this. Now, what is the magnitude property of this? We have seen the absolute gamma L. We are considering absolute gamma L, which is the magnitude of gamma z. So what will be that? You know, real part of ZL. ZL is the impedance. Since ZL is impedance, its real part is resistance. Resistance cannot be negative. Resistance has to be, or at best, it will be 0 or it will be more than 0. Therefore, real part of ZL is always greater than equal to 0. If real part of ZL is greater than equal to 0, then absolute gamma L should be less than equal to 1. Why it will be less than equal to 1? Let us see that. So, real ZL is equal to, as I told you, ZL is the impedance. So, ZL we can write as RL plus JXL. Impedance is Z is equal to R plus JX. So, taking that ZL we can write as RL plus JXL. Now, what is gamma L? Gamma L is equal to ZL minus Z0 by ZL plus Z0. For ZL, let us put RL plus JXL, then minus Z0 by RL plus JXL plus Z0. Now, what we will do is, in the numerator and denominator, let us combine all the real parts into one term, all the imaginary part into one term. So, in the denominator, real parts is RL minus Z0, imaginary part is XL. So, RL minus Z0 plus JXL. In the denominator, it will be RL plus Z0 plus JXL. Now, that implies that if I take the complex conjugate of gamma L, that will be RL minus Z0 by RL minus Z0 minus JXL by RL plus Z0 minus JXL. Or that you can also easily do it in another way, that multiply the numerator and denominator with RL plus Z0 minus JXL. So for gamma L is equal to RL minus Z0 plus JXL by RL plus Z0 plus JXL. The numerator and denominator, multiply them by RL plus Z0 minus JXL. Then the denominator will become RL plus Z0 square plus XL square, and in the numerator you will get RL minus Z0 square plus XL square. So that gives us gamma L square is equal to RL minus Z0 square plus XL square by RL plus Z0 square plus XL square. Now look at the numerator and denominator. In the numerator we have XL square, in the denominator we have XL square, and both are positive. XL square is added. And then we have RL minus Z0 square. In the numerator, denominator we have RL plus Z0 square, which means the numerator is smaller than the denominator. So since numerator is smaller than the denominator, gamma L square will be less than equal to 1, since the numerator is smaller than denominator. When numerator is equal to 0, it will be 0. Otherwise, it will, when the numerator is equal to, numerator cannot be 0. RL minus Z0, if that is equal to 0, then our RL plus Z0 is equal to 0. In those cases, it will be equal to 1. Otherwise, you will get it to be less than or equal to less than 1. So gamma L has to be less than equal to 1. This proves that gamma L is less than equal to 1. So remember this, gamma L, the upper limit on gamma L is 1. It cannot be more than 1. So this we know. Now gamma is the reflection coefficient. That is what we discussed. Since gamma is the reflection coefficient, and gamma is a complex number. If it is a complex number, it has a real part, it has an imaginary part. A real part we can draw on the x-axis, imaginary part we can draw on the y-axis, then we can get a complex plane. So for the gamma plane, gamma, we can, if we represent gamma on a plane, it will be a complex plane. So let us consider a complex gamma plane. So what we are doing here is, look at the figure. In the figure, this figure is for a lossless transmission line. We have along the x-axis we have real gamma, along the y-axis we have imaginary gamma. So that gives us a complex gamma plane. Now gamma, as I told you, gamma is equal to gamma z at any point z on the transmission line. That is what is gamma. So that we are writing as gamma r plus j gamma I. Gamma r is the real part, gamma I is the imaginary part. That also we are writing as gamma L into exponential j 2 beta z. Gamma L is the is due to the load. So gamma L is due to the load. It has an amplitude and it has an angle. So both of them are there. So that you can write as gamma L absolute exponential j phi L into exponential j 2 beta j. So that is the second line. In the third line, what we have done is, we have written that it is equal to gamma L exponential j, phi L remains as it is, then 2 beta remains as it is, then z becomes minus d. Why z becomes minus d? Because reference is taken on the load. From the load we have moved a distance d towards the left on the transmission line. Since we are moving towards left, it is minus z. So z we have moved a distance d, therefore it is minus d. So gamma phi L minus 2 beta d. So that we can write now gamma L absolute into exponential j phi L is equal to gamma L, that remains as it is, into exponential minus j 2 beta d. Now if I try to draw that, if we try to plot that on the figure, or if we try to draw this gamma on the complex plane, then what we will do is, first we will take gamma L, absolute gamma L from the origin, take absolute gamma L, draw a circle on absolute gamma L. So everywhere on the circle the gamma L can be available on the circle at any point. Now which is the exact point where we have to locate the gamma L or the reflection coefficient? That point is where the phase angle is phi L. So how do you find out phi L? Go from the real axis, move phi L is positive. Positive means we have to move in the anti-clockwise direction. Negative is we have to move in the clockwise direction. So move from the real axis, move in the anti-clockwise an angle of phi L. Then draw this line through this line. Draw the line from the origin, making that angle phi L. That will meet the absolute size or the length of that line should be absolute gamma L. So that gives you the circle. Dotted circle is that. So that point is your gamma L point. Now once we know what is gamma L point, we have to find out what is gamma Z point. Gamma Z point or gamma. Now gamma Z point and gamma L point, their relationship you can see in the 1, 2, 3, third line. Gamma L exponential j phi L into exponential minus j 2 beta d, which means we have to move from the gamma L point an angle in the negative direction by an amount of 2 beta d. So by an amount of 2 beta d, you have to move an angle in the negative direction. So that again, that shows you the red dot. So we have moved an angle 2 beta d from gamma L point to R point or gamma point. So the point gamma is the red direction, point red dot is the gamma point, green dot is the gamma L point. From first you locate the gamma L point. I hope that is clear. How to locate the gamma L point? Draw a circle. First draw a circle whose radius is gamma L and center is the center of the gamma plane, complex gamma plane. So first draw that circle. Then from the x-axis move an angle gamma L on that circle. The circle that you have drawn, that is the dashed circle. On the dashed circle move an amount gamma L in the anti-clockwise direction. So wherever that angle meets the dashed circle, that point is gamma L. Now from gamma L point move in the clockwise direction by an amount 2 beta d. So that is shown on the outer side. Outer side we have shown the angle 2 beta d. So move in the clockwise direction an amount 2 beta d. If clockwise direction means it is negative angle. Therefore, if you reach the new point, which is the red dot, which is gamma, now that gamma, if you go from the real axis to gamma point, then that angle will be phi L was the angle for the gamma L, and we have moved by an amount 2 beta d in the clockwise direction, so phi L minus 2 beta d. So that represents phi L minus 2 beta d in the angular term, and the absolute value is gamma L. So that gamma L exponential j phi L minus 2 beta d point is the red dot point. So this is how you will draw a point on the complex gamma plane. So remember, if we have a gamma plane or complex gamma plane, gamma means it is the reflection coefficient. So if you have a reflection coefficient point given to you, then you can always draw this. And on the dotted circle that you have drawn, everywhere on this dotted circle, gamma is fixed. So absolute value of gamma L is fixed. Same, absolute value of gamma L does not change, only the phase changes. Phase will be 0 if it is along the x-axis, or it is 180 degree from the 0 point. If you go to 180 degree, phase will be 0. Otherwise, phase will be any other value. Okay, so this is about complex gamma plane. We are going to use this complex gamma plane concept later. Now, we will go to the Smith chart or Z chart. Let us start with the Z chart, then we will come to other charts. Before we do that, let us take a break, 5 minutes break, and we will start with the Z chart. I hope you have been understood what is the complex gamma plane and how to draw a point on the gamma plane if we know what is gamma. If we know what is gamma, how to draw the gamma on the gamma plane.